So in this session today, we'll be talking about NSX-T design. And this session is focused on or fine-tuned for small to mid-sized data centers. And quick introductions before we get started. My name is Amit Aneja. I am a technical product manager in Network and Security Business Unit at VMware. I work on all the layer 3 routing edge design stuff and partially on the design side as well.
My name is Dumlu Timralp. I'm working as a systems engineer, part of the same BU, NSBU, covering global financial accounts across the world.
Thank you. All right. So just to make sure that we set the expectation right, this is not a 300 level session. This is a 200 level session. We'll not talk about how you will do some stuff. This is more to get you thinking as to why you should choose one design versus another one. So if you think that this is a deep dive, you're in the wrong session. But there are definitely sessions which are deep dives, which are covering each of these topics. And there is another design session, I think, after this one, which Nimesh is covering, where he kind of goes into detail into the whole enterprise data center design. So let's get started. So today we have a packed agenda. We'll try to finish 5 minutes before the timer and leave some time for questions. But in case we run over time, catch us outside. We have no more meetings. Both of us have no more meetings. Catch us outside if you have a question, if you think you relate with these kind of designs, or if you have NSX-T in production, or if you are thinking of deploying NSX-T in production, catch us outside and we'll be happy to whiteboard with you or answer any questions. Now, before we go through the agenda, how many of you have NSX-T in production, have NSX-T deployed? Okay. Very nice. How many of you are NSX for vSphere customers? Okay, very nice. Now, how many of you relate with the small to mid-sized data center? Let's look at the small one. And when I say small, I'm talking about 10 hosts or less. Is that your definition as well? Okay, great. So there are no real definitions. You can't really put a number to it, but this is what our discussion is based on. 10 to 50 hosts or something like that. So we'll cover the NSX-T platform basics, more like the architecture, but this is a breeze through. There are dedicated sessions for this, just to make sure that everybody is on the same page. How many of you have never gone to an NSX session? Okay, very nice. I am impressed. So, and then we'll cover, we'll define the numbers, like what is how does NSX look in the data center, right? It's very basic, so it'll be a quick walkthrough as well. Then the meat of the presentation is the design considerations. We'll talk about compute. How should you design compute, edge, management? How should you place edges? That's a question that keeps coming up. Then Dumlu is going to take over and talk about vSAN considerations, reference architecture, like how other reference architectures are using the same designs, the same design principles under the hood. And then we'll talk about how do you grow, and we'll take questions after that. All right. Now, I'm sure that you've seen this slide. All this to say here is that with NSX-T, we have decoupled NSX from vSphere, from ESX, so that NSX can integrate with NSX can provide that consistent networking and security stack for all your applications, regardless of where you run it, whether you're running it on-prem, on KVM, ESX, or whether you're running it in AWS, Azure, VMC on AWS, NSX can provide you that consistency. Now, with NSX Intelligence and VRNI, we can provide you deep insight into your network as well as your application level as well. So, moving on. This slide shows you how NSX-T solution can provide you that consistent networking, consistent security stack across all these heterogeneous endpoints like VM form factor, containers, bare metal as well. If you are running VMs, right, most of the companies are investing into microservices, into containers, right? For a small to mid-size data center, like if, let's say you have 10 hosts, right, and you want to invest in containers, you have developers who want to go the microservices route, right? But you have a smaller team. You don't have expertise. I mean, smaller data center comes with smaller teams with a skill set that has, that's not very unique. So you have to handle everything. So the purpose of the slide is that with NSX, you get the consistent networking stack, meaning the routers, the switches, all the 9 yards like load balancer that you get for VMs. You get that for containers. You get that now if you plan to grow in AWS, Azure, you take those constructs there as well. You plan to grow in VMC on AWS, you take those constructs with you. And one more important point is the security posture, right? You define policy once for VMs for your environment. Now, let's say you have a web VM, it's a virtual machine. You have a couple of bare metal boxes, and you have you have containers as well. You define your policy that would be pushed to the VNIC level on each of these. VNIC on the VM, your pod networks, the container networks, and your bare metal as well. And then we have rich integration with PKS, PAS, and OpenShift for your container platforms. Now, moving on, and I'm sorry if you have seen the slide earlier. This has been used in a couple of sessions, but I wanted to keep this slide. This is to say that yesterday I had a Meet the Expert session for routing, and somebody asked me, why would I need distributed routing? I mean, I have my top-of-rack switches doing routing, and I have no problem if the packet goes up from hypervisor to the top-of-rack and get routed and come back. They have no problems with that. So my answer was, you don't need distributed routing. Distributed routing is an advantage. You don't buy NSX for distributed routing. You have to solve a bigger purpose, a bigger business case. So NSX is a SDN platform. It's a solution that will provide you a rich set of services with all the fancy routing features, VPN, both L2 and L3, IPsec VPNs, load balancer. You have L4 and L7. That would be, and you could natively use this load balancer for Kubernetes environment as well. Firewalling. This becomes important as well because you are doing, most of our customers are using NSX for micro-segmentation. That has been the classic use case. So putting the policy at the VNIC level, that becomes really important. But there is another use case for this. Of course, you have a dedicated firewall at the perimeter, right? Nobody removes the firewall from the perimeter. But for your east-west security between your tenants, you can use the gateway firewall here, okay? You don't have to buy more firewalls and plug it into your network for east-west separation. Connectivity to physical, all the services like NAT, DHCP, IPAM, metadata proxy for OpenStack users. Now, there have been sessions about each one of these services, each of these. So this is from all the NSX TPMs, the technical product managers. So I recommend you watch these sessions if you have not attended these. I'll give you a minute to take a picture. All right. Let's move on. All right. Damlu? So let's talk about the priorities of a small, medium, mid-size data center. And by small, mid-size, when we say small, mid-size data center, that doesn't mean that your company is small. That means you could have multiple islands of NSX. That means you are going pilot with a small deployment, and then you'll grow in future. So the priorities are different for a small to mid-size data center.
And what we see in the field when talking to our customers is those priorities, those design decisions usually boils down to these three main categories. One is physical footprint, which becomes extremely critical, especially in the small and medium data center context. The reason is it can easily be a colo place in which you may be paying for square footage or for one tile, a certain amount of cost. And in that sense, NSX helps a lot with the virtualized network functions, because rather than putting a dedicated physical appliance for load balancing, firewalling, etc., you can save up space, which would be beneficial for you in an NSX-T-based small and medium data center design. Then what we are also seeing is in a small, medium data center footage, it is usually not being maintained and managed by tens of different engineers. You don't get to have a dedicated firewall management admin or a load balancer admin. So in that sense, the operational tooling becomes extremely crucial in terms of maintaining and operating that environment. That's what we are providing with NSX, the same UI for different kinds of networking functions that you would want to use in the same environment. But with that, there is also a huge aspect, an important aspect, which is with overlay networking, with decoupling your networking intelligence from the underlying physical fabric, what you can do with firewalling on top of it, with distributed firewalling, is collapsing your different kinds of environments or zones into the same ESX cluster or clusters, which once again helps you with the physical footprint aspect as well. Which also brings us to the cost topic within the design decisions space. The reason is, with cost, NSX can be licensed per CPU socket, so you can utilize your individual physical servers as high as you want. In terms of that, it brings you different benefits by using licensing per CPU socket. The overhead piece, I'm going to dive into it in the next slide, which is, you must have gone through this usual exercise of, I have some number of VMs which will land on a certain amount of ESX host landscape. In this example, really quick, I don't want to get into each and every number here, but 200 VMs, considering the average vCPU, average VRAM size for those VMs, we find ourselves in an 8-host based ESX cluster. But as soon as you start utilizing this cluster to more than 90%, then you have to take into account the availability aspect right away. What we recommend is a +1+1 approach, which means +1 for failure and +1 for maintenance. But again, it comes with its own cost, or it comes with its own different design approach, which is, we added 25% of overhead into our architecture. For good, but for a reason. And also, when you gear towards the more enterprise data center design by segregating your management and edge resources in a separate ESX cluster, that means a separate, at least a minimum of 3 host-based ESX cluster for your management and edge resources. But again, the same principle may apply, which is availability, providing the availability for that ESX cluster, which again means that +1+1 approach being taken for that ESX cluster, that will add more overhead in your environment. These are the things that we are going to walk you through when we are talking about the design aspects of different components in these environments.
Perfect. Thank you, Dumlo. So just one key point, and your maths does not have to be exactly like ours. These are just rough numbers. Your VMs could be larger, your VMs could be smaller, but these are just rough calculations, something that the VI admins already do. Just focus. The idea of this slide is to focus on this part, wherein you had a single cluster. You were running single cluster, meaning a collapsed cluster, and we'll get to what is a collapsed cluster. You were running with 25% overhead. And when you separate out the cluster, when you host management and edge components in a different cluster and compute in a completely different cluster, your overhead for the same compute workloads becomes 37%. Okay, so this is something to keep in mind. And you could come to a different design decision as well based on your environment. So something to keep in mind when to go shared. When to share a cluster and when to go use separate clusters. Now, we wanted to kind of put some numbers out there as to what we think this talk will focus on, and what is my definition, what is Dumlu's definition of small, mid-sized data center. Now, your numbers, again, could be different. We are just focusing on. This is to show you what is the thinking process. I'm pretty sure that all of us are smart guys here, including me. So we have done this math and we have gone through the process. But what is a small data center? So we are thinking, when we call small data center, we are saying 4 to 10 hosts, 1 to 2 vSphere clusters, and typically you're hosting workload VMs, 100 to 250 workload VMs. And your north-south bandwidth is almost in all the scenarios that I have seen is less than 10 gig. Let's move on to mid-size data center. Mid-size, wherein you have a 10 to 100 hosts, vSphere clusters increase 4 to 10, and your workload VMs increase to 1,000 to 2,500 to 3,000 range. And then your north-south bandwidth, in this case, it could be greater than 10 gig, or it could be less than 10 gig as well. We'll talk about both use cases. What should you choose in either of the scenarios? And then large data center, again, you could have thousands of VMs, 100 plus hosts. That's the area we are not focusing on in this session, okay? Now, let's quickly breeze through architecture and terminology so that everybody is on the same page when we talk about compute and edge, okay? So the purpose of this slide is here to just simply say that all NSX really needs is the IP connectivity. If you have L3 connectivity, you can have any fabric, any topology. If you're running leaf spine today, if you're running super spines, if you're running core access AG, we don't really care. Of course, the forwarding matters. Your physical fabric matters, but we don't care. All we need is the tunnel endpoint to tunnel endpoint connectivity and a MTU, because MTU of 1700, because we are encapsulating those packets in overlay. So we need that MTU of 1700 bytes. We recommend that you do, when you're doing this change, might as well just do a jumbo frame. Do a 9000 MTU so that you don't have to go and change every other switch after that. Moving on to the architecture. So NSX-T architecture has 3 planes, data plane, control plane, and management plane. In the data plane, this is where your actual forwarding happens. This is where your workloads are. If you have VMs, containers, or sitting on ESX, KVM, or bare metal server with the NSX agent installed, or a NSX edge. And we'll double click on this NSX edge, okay? So these are your transport nodes. Anything that switches your data plane traffic, your actual traffic from your workloads. And in the public clouds, we have equivalent, but I'm not going to cover this because this is not relevant for this session. It's, again, Linux VM, Windows VM, or a flavor of edge VM that translates into a cloud gateway, NSX cloud gateway. Moving on, up the stack, we have a NSX controller. What does this NSX controller do? It is, I like to think of this as a brain of the system, overall brain of the system. This controller has a job of, it would know at any given time where a VM is, where its MAC address is. One job is to push the configuration downstream to the transport nodes so that the data plane nodes have that configuration. Another one is to extract that information out, like a specific VM or all the R, MACs. They would be learned by NSX controller. So if I learn it from one host, I am going to give it to another host based on the type of host, so that everybody is aware of where everything else is. It could be pull or push mechanism as well. On the top, we have NSX Manager, which is the UI or API endpoint. This is where you configure stuff. This is where you store your desired configuration. Okay? This is the place wherein you would integrate with vCenter or any other compute platform or any other like OpenStack. You know, this is where you would. We have some inbuilt plugins like NCP. This is how it integrates with Kubernetes. Now, starting with 2.4, we are on 2.5 release today. Starting with 2.4, we have merged these two appliances, the controller and NSX Manager, in one appliance. We call this unified appliance. And now you have 3 VMs which are doing the job of NSX Manager and controller, okay, for scale out and redundancy. Moving on. Now, just right off the bat, I wanted to start with this slide. What is a transport node? When I say transport node, that NSX-T transport node is any node that has NSX installed on it, NSX VIBs installed on it, and is also configured for a tunnel endpoint. That means it can encapsulate overlay and it can decapsulate overlay. Okay? So what do I mean by transport node again? When I say we install NSX bits on this host, that means we install a switch on this host, NVDS. That's your NSX V switch. Okay? So, and that's where we'll configure the tunnel endpoint as well. Now, this is a virtual switch. Just like you have VSS and VDS, they don't share physical NICs, right? So NVDS also cannot share physical NICs with your VSS or VDS. It can coexist with VSS, VDS, or any other NVDS as well, but it doesn't share the physical NIC. So in this case, all your VM kernel traffic will flow through VDS. All your overlay traffic will flow through NVDS. Okay? And we support both overlay and VLAN segments on segment, meaning the logical switch on NVDS. Okay, moving on. So we talked about an edge node. This edge node is also a transport node. So what is the edge node? This edge node is just a service appliance that has a couple of resources, and then you are spinning up, this is your north-south gateway. When you connect to your physical world, when you connect to your top of racks, this edge node is the one which is connected to physical world. Now we have two form factors in this. First is a bare metal edge node, and bare metal edge is simply a hardware, and you install edge ISO on top of it, okay? Edge software on top of it. And next up is VM form factor. I mean, what is the edge VM? It is simply a VM with a couple of VNICs, and it can sit on VSS, VDS, or NVDS. I'll come to this NVDS part because this becomes really important in case of a collapsed cluster design for, let's say, a 4-node cluster. So edge VM, basically a VM with NVDS installed and can run on the over VSS, VDS, or NVDS. Okay? And it's also a transport node, meaning it can encapsulate and decapsulate overlay packets. Now, this is one slide from my previous session on the routing. How should you think about logical routing? How should you, when you are creating logical routers, we have support for single-tiered routing. What is single-tier? When you have your logical switches, when you have your layer 2 broadcast domain where your VMs are connected, you connect it to a logical router, okay, or a gateway, and then that gateway talks northbound to physical infrastructure as well. That's single tier. In this case, I have 2 tiers of routers. First one is tier 0. Now, this tier 0 is more of an admin router, a provider router, which would talk to your northbound devices, which would talk to your physical boxes. This is where you would run BGP, static routing, and do all the fancy configurations, right? Now, what is the role of this tier 1? This tier 1, it depends on how you want to consume it. I'll give you an example. Like, if you have different departments in your organization, prod, dev, marketing, HR, put them in different tenants. There is another use case for service providers, managed service providers. Like, if you want to give them some kind of control wherein they connect some segments to it, or switches or workloads to it, and they advertise you your routes. And then you as an admin, get the full control on the tier 0, whether you want to advertise them further northbound to the physical infrastructure or not. So there is one more advantage here, that you touch the physical fabric once. You can bring in new tenants, you can onboard new tenants, destroy tenants once the work is done, and you don't have to touch the physical fabric. It's just a BGP update message at that point. Okay? All right, let's talk about NSX in a data center. How does it look? So just to give you some idea as to how does NSX look like when it is installed in a data center. Herein on the left, I have compute clusters. All of them have NVDS installed, which is our virtual switch, NSX virtual switch. Over here, I'm using a edge cluster, a separate edge cluster, which could be bare metal or VM form factor. And I have a separate management cluster. I've seen a couple of large deployments using this, but this is not for small to mid-sized data center. This is just to show you that all your distributed routing, distributed switching, distributed firewalling, it happens here on the compute cluster, right? All your centralized services, like when you enable NAT, when you enable DHCP, or when you want to connect to the physical world, all the services, they get realized on the NSX edges. This is where the traffic would come to go out, to exit out of your data center. And over there, I have a management cluster, which is basically hosting vCenter, vRealize, or NSX managers. Okay. Now, this is not feasible in all the circumstances, right? You'll have dedicated service appliances here as well. Let's move on to what I call a mid-size deployment. In this case, if you notice, the compute cluster is the same. I have two vSphere clusters. It could be KVM clusters here as well. And all of the clusters have NVDS installed, okay? Whatever PNICs you have, like if you have 4 PNICs, 2 PNICs, 10 PNICs, NVDS will take it. Now, in this case, I'm using a shared cluster, shared management and edge cluster. So I'm hosting the edge nodes, the one I'm showing in green, on the same cluster, okay? Now, the edges could be VM or bare metal form factor in this case. I have seen a few of my customers who are running bare metal in a mid-sized data center. Their primary use case is the convergence. They expect low convergence north-south. Typically, they have applications which can't survive more than 1 second of failure. In those cases, I recommend use bare metal, but VM form factor, if that's not your use case, if you don't have those applications, VM form factor does the job for you, okay? And you would notice that NVDS is not installed in this, meaning these hosts are not prepped for NSX. These hosts are just ESXi host. You have a VDS running, and you have done nothing from NSX side other than installing a couple of VMs, NSX Edge VMs and Manager VMs. Now, in this case, you would leverage you would have a dedicated firewall, of course, but you will leverage NSX-T services kind of in conjunction with those services. You could have a F5 load balancer that would be used in conjunction with NSX load balancer. Let's move to a smaller design. In this case, when you have 4 hosts or 6 hosts in your cluster, what do? You can't dedicate hosts for your management and running edges. So what I have here is that vCenter, NSX Manager, NSX Edges, they all sit on NVDS. They all sit in the shared management edge cluster. Each host would have a VDS installed. Now, this is ESXi only design. We do not support Edge VM on KVM today, so this is ESXi only design. Edge would always be VM form factor, and you would leverage NSX-T services heavily in this design. I mean, in a smaller data center, you don't have the luxury of buying dedicated devices. So you would, if you are not, and if you have NSX-T and if you are not leveraging those services, you should. And again, important, each host would have NVDS installed. Now let's double click into this design, okay? I'm going to take one host and show you how it looks like. So I'm starting with a 4 PNIC design. I took one host, and I'm assuming that that host you had was that had 4 PNICs, right? A lot of customers have our 4 PNICs. So in that case, I have my NSX Manager sitting on VSS or VDS, my VM kernel sitting on VSS VDS, and my Edge VM is also sitting on VSS VDS, okay? And then you have your compute workloads which are going through your NVDS. Now, very important thing that you should note is that both of them are tunnel endpoints. Your edge is also a tunnel endpoint, and your compute host is also a tunnel endpoint. They'll form an overlay tunnel between them, right? The VLAN that I'm showing here is VLAN 75 on the compute side. The VLAN that I'm showing here is also VLAN 75. When your edge VM is not sitting on the same NVDS, you could have the same or different VLANs, okay? This can be done today. Now, let's move on to in this case, all your, just to finish on this, all your management traffic, VM kernel traffic will go through PNIC P0 and P1. All your overlay traffic goes through P2 and P3, okay? Moving on, what do you do when you have 2 PNICs hosts and you have a small data center? You are left with no choice but first to bring your vCenter, NSX Manager on NVDS. You have no choice but to bring your VM kernels on NVDS. And we have a kind of a migration wizard. So if you have a 2 PNIC host and you are installing NSX, so we have a migration wizard which would detach, which would bring the VM kernels onto NVDS, okay, during installation. And in this case, Edge is also sitting on the NVDS. Now, in this case, when an Edge VM, which is also a tunnel endpoint, a transport node, is sitting on top of a NVDS, these VLANs, the VLAN that I'm showing on the Edge and the VLAN that I'm showing on the compute transport node, they cannot be the same today. So you have to plan for an additional VLAN. Now, the reason why we don't support this is that this is a VM sitting on the hypervisor, this edge, and it is generating overlay traffic to a VM kernel interface. Today, we think that's kind of an attack, so we don't allow this communication. And several of our customers have asked us that are we trying to remove this? So we are trying to remove this limitation because some customers told us that it's not possible to talk to physical guys, get another VLAN or something. So we are trying to remove this as well once we have a simpler answer from engineering. All right, so let's talk about the design considerations. Oh, I'm way over time. Okay, so let's talk about management cluster. So this is a summary slide of how you should think about, what should you think about. Start with management cluster. How should you size the NSX manager? In smaller environments, the size of the VM really matters. You want to give more resources to your compute, and of course, you want to make sure that the compute resources run fine. So small NSX manager comes in various form factors. Small is just for POC, don't deploy it in production, it's not supported. For medium, it supports up to 64 hosts. Large is 64 to 124 hosts. Whether they should be on the same subnet or a different subnet. In small to mid-sized data centers, I see no reason why your three NSX managers can't be on the same subnet. Don't do it. Don't make your life complicated. Put it on the same subnet. These are just 3 VMs. And we'll talk about whether you should have a 3-node or a 4-node cluster. For edges, what should you consider about? Throughput, primary design consideration. This is the factor that will help you choose in your VM versus bare metal edge form factor. Convergence, really, really important. Bare metal edge versus VM form factor edge. Bare metal edge gives you less than 1 second of convergence, north-south convergence today, because we support a BFD interval of BFD interval of 300 milliseconds. That means your BFD goes down in 900 milliseconds, and your convergence is less than 1 second. A VM form factor, 3+ seconds, because the BFD keep alive timer is 1 second there. High availability. Should you have different edge clusters and failure domains? I'll talk about this in detail. And what should you think about compute cluster? How many PNICs you have? What is the teaming policy that you're choosing? Failover order or source port? And where should your VM kernels live? Can they live on NVDS? I showed you, yes. All right, let's start with design considerations on management. And I'm going to just quickly speed up because I'm running late on time. So a lot of customers ask this question. What is the latency between NSX managers? What is the supported latency? It's 10 milliseconds. So the way they ask this question is, can my NSX managers live on different sites? Yeah, if you have less than 10 milliseconds of latency, yes, we support that. Yeah, you should have vMotion support for NSX managers. You must use vSphere-based cluster management like DRS, and you should have anti-affinity rules. So in case one of the manager goes down, anti-affinity rules is when you spin up the NSX manager, they don't end up on the same host, right? And they should be marked as should, not must. So just in case other host dies, the only choice it has is to be hosted on the same host, right? Loss of a single manager is acceptable. When you lose 2, there'll be no topology changes. It's read only. There'll be no vMotion at that point, okay? So that's why we suggest that you have 4 hosts in this cluster, in the management cluster, so that you can take one out for maintenance or failure, okay? We're not overkilling it with +2 here. All right. Let's move to, I'm just going to breeze through this slide. We have 3 modes of management cluster. Like, they can be in the same domain. In this case, you can send your API calls or do the UI configuration on each one of these. This one is the old way. We don't want that. Like I said, you want to use for a small mid-sized data center, this is a cluster web. This is a virtual IP. So when you are you're going to 10.1.1.1, and your managers are 10.1.1.2, 3, and 4, right? And it'll redirect those calls to one of the members, one of the NSX managers. For small to mid-sized data centers, this is our recommended approach. There is no UI or API load distribution, but then you aren't making a zillion API calls in this case, right? And this requires that they are on the same L2 subnet. There's another way wherein you could have a load balancer if you want UI or API load distribution as well. You could use that. No, you should not for a small to mid-sized data center, because there you could have managers in L3 subnets, different L2 subnets. Moving on to compute. Okay. All right. So, like I said, we've talked about this slide before. You have your VSS or VDS where you have your VM kernels. This is a 4 PNIC host, and then you have your NVDS that's hosting your overlay traffic. Okay. Now, what should you think about in this case? Again, the second ESXi node with only 2 PNICs. In that case, we give you no choice, right? I mean, you could separate out 1 PNIC for VSS or VDS and 1 PNIC for NVDS, but that wouldn't really make sense because you have redundancy for nothing in that case. So in this case, you bring all your VM kernels and your overlay on NVDS. What should you think about? Teaming policy. We support 2 teaming policies: failover order, which is active standby, meaning I'm talking about the NVDS policy, meaning one of the uplinks or one of the PNICs is going to be used. Source port. This is a recommended policy for your compute transport nodes so that you optimally use both of your uplinks and eventually PNICs, right? This policy is not supported on KVM. Now, very important, and it often gets left out, name teaming policy. This is a real important concept. What does this do, name teaming policy? It pins traffic to a specific uplink, and I'll get to that in next slide. What is name teaming policy? Now, I'm taking an example of a 2 PNIC host, right? In this case, your overlay traffic would follow your default policy. The overlay traffic says, okay, well, based on this, the uplink profile that you configured, it says active uplink is U2, uplink 2, and standby is uplink 1, okay? But is that optimal for your management traffic? You don't want to send it through the same policy, right? You want to be able to, just like in VDS DVPG, you say, okay, now this is my uplink for this specific VLAN. So in this case, I'm saying management traffic, go active on uplink U1, standby on uplink U2. vMotion, I could simply say go on one uplink, right? So this is just to say that this is supported for VLAN segments or your VM kernels. You can pin the traffic to a specific PNIC or a uplink interface, okay? And I'll get to the use of it, where we use it. All right. Now, I wanted to show you that this is how you configure it, so I wanted to keep it as a reference, that this is how you configure name teaming policy. All right. Let's talk about edge. In edge, we have 2 form factors. Like I said, bare metal edges and VM form factor edges. In small to mid-sized data centers, I have mostly seen 80% of my customers are running VM form factor edges. Now, what are the design choices? Like I said, cost. It's just a VM, right? Using NSX licensing, but it's leveraging vSphere. You have to have ESX as well, right? We don't support it on KVM. The deployment is simpler, and you can simply install it from the NSX manager. You don't have to have special purpose hardware. The performance is pretty decent on the edge VM, and considering that we support 8-way ECMP, so you can go all the way to 70, 80 gig throughput, right? And even if that doesn't scale, we can throw in another edges and still scale it up. Bare metal edges is like high throughput. We support 10 gig NICs, 40 gig NICs, 25 gig NICs on bare metal edges, right? And so the cost is an interesting part on bare metal edges. So I want to make sure that you guys understand this, that it's on a low cost server like 32 gig RAM, 8 vCPU, and 200 gig hardware, 200 gig hardware box. It's not really that expensive proposition. You're not using ESX licensing here. There is no vSphere licensing. All you're using is NSX license per socket. So if you have applications that require sub-second convergence, think about this. It's not an expensive proposition from a VM form factor. All right. let's talk about, in Edge VM as well, we have various form factors, small, medium, or large. Small, it's POC only. I would go with medium for small to mid-sized, small deployments, okay? Because you have, I think we have enough number of LB VIPs, you have enough number of VPN sessions that you would need in a small data center. For a large, for a mid-sized data center, I would go with a large Edge VM. It increases the scale, it increases the number of VIPs, it increases the number of your IPsec sessions. Now, let's say you have made the choice today to a medium. It doesn't mean that you're bound to it. There is a simple workflow which a lot of people miss, is that you can simply replace a medium edge with a large edge. So this is not a lift and shift. You simply say, okay, I want to just, and this is really the screenshot from UI. You replace a medium edge, and all the resources that you configured in medium edge, they move to the large edge. Okay, really useful feature. Yes.
Can you replace labs to medium if you?
Yes. So the question is, can you do it the other way around? Yes, you can do that. You can also replace this with a bare metal edge. You bring a bare metal edge into the cluster, and let's say you started with a POC, and you say, okay, well, it works great, which it will, and you can replace it with a bare metal edge.
But this also means that you don't have to overkill the design from day zero by going,
Yes.
by moving forward with a bare metal edge.
Okay, great. So, and this is how do you route? How do you connect to the physical world? And this is a really touchy-feely topic for a lot of hardware people who have lived in Cisco land, Juniper land. I come from that land as well. So, should you do VPC? Should you do routing over VPC? And I know from experience that all the hardware vendors have solved these problems. They are supported on a specific hardware module. They are supported on a specific OS version. And if all the stars align well, yeah, it's fine. It's not a recommended choice. Don't do routing over VPC. It's not recommended. If you have compute host, great. This is just for the edge. You see that this is a edge bare metal which is hosting your tier 0 going northbound. Instead, we recommend that you use the name teaming policy that I showed you. Do not reinvent routing connectivity. Use name teaming policy. And what I mean by name teaming policy is that you say, okay, well, I am establishing my VLAN 300 BGP peering connectivity with top of rack 1 here. So from tier 0 to top of rack 1, VLAN 300 BGP connectivity. From tier 0 to VLAN 400 on top of rack 2, VLAN 400. This is point-to-point BGP connectivity. And believe me, your life would be much, much simpler rather than trying to figure out when something goes wrong. Oh, where is this traffic going? So you go to the CLI and you do a ether channel hash and say, oh, it's going here. And half of the times you will struggle to find that command. Where is the traffic going? So use this name teaming policy. It is much more deterministic. When something goes wrong, you're like, okay, well, this adjacency is down. So you know that there is a problem with VLAN 300. There is a problem with either the tier 0 or the top of rack 1. So you don't have to just wander around. All right, moving on. This is a screenshot that I wanted to show that, again, name teaming policy. In this case, I'm routing external. I'm spinning VLAN 300 to top of rack 1, pinning VLAN 300 to top of rack 2 using uplink 2. Okay. Let's talk about services availability. The edge cluster availability. So we support gateways, the logical routers in active-active and active standby mode. If you are in active-active, you can't run any stateful services. Okay? The stateful services are only in active standby. Moving on. This is just a recommendation, quick recommendation. When you are running services, centralized services, run your centralized services on tier 1s so that they are in active standby at the bottom, but your top layer still can be ECMP, okay? So that you don't compromise on your north-south bandwidth. All right, let's continue moving. Last concept that I'll introduce is failure domain. This is fairly new. This is what we introduced in 2.5 release, okay? So what is a failure domain? Now, before even that, you will hear in a couple of design sessions that we have today that I think Nimesh talks about whether to use a shared cluster or a dedicated edge cluster for running services and your north-south. So some people do separate it out. Like if you are a heavy LB user and if your north-south bandwidth is high as well. So they do separate out the edge clusters. It's possible. But for a small or mid-sized data center, I don't see a reason why you should. Use the shared cluster. You want to save on the resources. Next up, how do you provide for redundancy? Let's say you have one rack wherein you have two edges. Now, if this rack fails, all the services are gone, right? So if you have the luxury, spread it across the racks, okay? Only if you have that luxury. Now, in this case as well, it still doesn't guarantee that when I create a tier 1, that will not, the active will not go here and standby will not go here. So we came up with this new construct called as failure domains, which means that now when I create a tier 1 logical router, if I have load balancer on it, the active would go in failure domain 1, standby would go in failure domain 2. If I create another tier 1, failure domain 2, failure domain 1. So that provides you against rack failure, overall services availability. All right, I'm sorry, Dumlu, you have 15 minutes. So we'll talk about vSAN considerations and the reference architectures, which are using the same architecture, same baselines that we have used under the hood.
So failure domain topic takes us to the storage layer, actually. And what we are seeing in the field is vSAN is becoming almost the de facto standard for the SMB design. Really quick, since I have the, not 15, but 14-minute challenge. In terms of availability, as I mentioned earlier on, what we recommend is a minimum of 4 nodes in the management cluster. And the reason for that is actually, I said 3 nodes earlier on, but since you have 3 NSX managers in the cluster running, you would still want to run an ESX host maybe in the maintenance mode and then still tolerate a failure. So in that sense, what we are gearing towards is a 3+1+1 design. And in that design, what you will have is an FTT of 2. For the ones who are not familiar with the FTT concept, it's the failures to tolerate, which is 2. And FTT2 means is you are writing the data to 3 different hosts at all times. With that, what you have as a benefit at the same time is, as I said, you can not only run one ESX host and put it into maintenance mode and tolerate a failure, but also when you are putting that ESX host into maintenance mode, we highly encourage you to vacate the vSAN data on it. It makes the process a bit longer, putting the ESX host into maintenance mode, but it is a much safer method to keep your data intact. The physical placement becomes also quite interesting, because you shouldn't place all your ESX hosts, or you shouldn't place a certain number of ESX hosts into the same failure domain if the number of those ESX hosts are more than your FTT value. So with an FTT2, which means if you have, as mentioned on this slide, when you have a 6-host ESX cluster, you shouldn't put more than 2 hosts into the same rack if you are talking about a rack failure, or if you are designing the whole architecture by taking into account any kind of rack failure, any kind of top of rack failure scenarios. In this case, with a 6-host ESX cluster, you would spread that cluster across 3 racks. But when you have a layer 3 fabric underneath, then you need to take into account the load balancing topologies or the scale-out nature of the NSX manager cluster into account, in the sense of you will have to put a load balancer in front of the NSX manager cluster to spread your API requests and your management requests. So when it comes to edge node VMs on top of a vSAN IP storage layer, what you need to take into account is those failure domains that Amit recently mentioned. You would want to align your storage layers failure domains to the edge node failure domains to each other. And the way to do that is, again, taking into account the design that you have chosen from the earlier step, which could be FTT2, and put your ESX cluster and spread it across racks. Or it could be a vSAN stretch cluster across racks with a witness. Or it could even be multiple vSphere clusters based on your design choice, obviously, because this is an SMB session. You may not want to overkill the design from day zero by using multiple vSphere clusters just for edge nodes. Again, physical placement is an important thing in this aspect. The reason is when one of your edge nodes fails, then you still need to take into account whether if there is a layer 3 fabric underneath or a layer 2 fabric underneath, because when that edge node runs in another rack, when it gets recovered, you still need to have the appropriate peering, root peering VLANs on that other rack. In a layer 3 fabric scenario, you won't have that same VLAN ID, you won't have that same subnet IP address space on that other rack. Reference architectures. This slide is showing you what we are looking at here is the typical VMware Cloud Foundation or VMware validated design approach. Let me ask you this controversial question when I have 9 minutes left already. Is this a good or bad design, you think? Please raise your hand if you think this is a good design. Please raise your hand if you think this is a bad design. The right answer is, there is no right answer, because we are talking about virtualization layers here. There are too many design choices. You have to make not a choice, but multiple choices, depending on your design considerations or design constraints. Yes?
The interesting one about this one is one of the few places where collapsed compute and edge is mentioned. Because most of the places mention collapsed management and edge, which feels weird to me coming from V. And this is much more logical, but it's one of the few places that this is mentioned.
In that context, there is a difference with NSX-V. I don't want to go into that topic right now, but because of that difference, the placement may differ between NSX-V and NSX-T. But what I was trying to elaborate on is, with this design, the design approaches segregating maybe the SLA levels, segregating the management boundaries between the NSX edges and your management domain. As you can see, the NSX edges in this architecture is running those edges in the compute clusters. And the thing that you may benefit from this is, again, you may have different tenants in the same compute cluster or compute clusters, and you may want to provide the same level of SLAs to both the data plane and also the compute layer for each and every of those tenants. And you may want to segregate your management domain completely into a different set of racks from that domain. That could be the design approach that you want, or what we have with Dell's Pivotal Ready architecture is, which is, again, this is a Dell EMC offering in conjunction with VMware and Pivotal solutions. On this kind of an approach, what we are capable of doing is running Pivotal Application Service solution or Pivotal Container Service solution on top of this kind of a design. And as you can see in this design, where this design is placing the edges on is the collapsed management edge cluster. But guess what? That management edge cluster is being spread across multiple availability zones. Which specific thing has been the driver of that multiple availability zones? Well, it has been the compute layer. Because in the compute layer, guess what? We are running cloud native workloads. So what I'm just trying to say is, there is no right or wrong answer to these designs. It all depends on the design constraints and the design decisions that you need to make based on either the workload layer or the compute layer or the storage layer. Or the data plane of the overlay solution, which is NSX-T in this case. But again, as you can see, here there is a huge difference in a sense that we are placing three completely different compute clusters, one per availability zone, but at the same time, we are spreading across our same management and edge cluster across those availability zones. And again, these two designs are completely different from each other because they are based on different design constraints, different design decisions. With that, quickly, I'd like to cover the VxRail aspect of this. The reason is VxRail comes with its own design constraint, which is a VxRail node when you want to use an NVDS on it, you have to use 4 PNICs on that VxRail host. The reason is the VxRail management plane, VxRail manager, is using the 2 PNICs of that ESX host for its own management plane to segregate the traffic, to steer the traffic through those PNIC 1 and PNIC 2, which are based on a VSS or VDS. So in this design, as Amit mentioned earlier on, you would put your overlay traffic, your workload traffic onto the NVDS and run your workloads traffic through that NVDS through PNIC 3 and PNIC 4. As you can see on the left bottom side of this slide, VxRail also manages the name teaming policies or the teaming policies on the VSS or VDS on the left-hand side per different types of traffic, like vMotion is using uplink 1, vSAN is using uplink 2 in this case. Really quick, in the last 4 minutes, I'd like to run through these design questions that may come to mind, like how many VMs you are going to be placing in your data center, what kind of a P2V project or what kind of a P2V capacity are we talking about here, how much you are going to utilize or overutilize your ESX hosts, because it will have an impact on your license per socket cost approach. The reason is, with license per socket CPU or per CPU socket, you can overutilize your ESX hosts with the least amount of licensing costs. So again, what we mean by this is usually less than 250 VMs usually means a collapsed cluster to us. Which means 25 to 50 VMs usually gets RAM constraint. But again, the same point, socket licenses means larger hosts that you may want to use, which you are able to utilize more though. What types of failure you design for? What I have seen as an individual, not as a VMware employee, but when taking my VMware hat off, the layer 3 and layer 2 fabric approach becomes quite interesting to take into account in your design. And also, when you are spreading your cluster across the racks, again, the same failures to tolerate design considerations come into the picture. You always need to keep in mind that you shouldn't violate the principle of FTT when you are trying to provide an ESX cluster-based redundancy across racks. In that sense, the bandwidth management per physical NIC, per ESX host becomes interesting with that VMware Cloud Foundation or VMware validated design approach, because remember, you are putting your NSX edges into your compute clusters. So you need to take into account which edge would consume what kind of bandwidth so that you can provide enough bandwidth on the ESX host or hosts which you are running your NSX edges on. With vSAN or traditional storage approach, what I need to highlight on this specific slide is, with the HCI storage, that means usually less VMs per host to provide more hosts with a higher resiliency in your architecture. With bare metal or VM-based edge design topic, what I tend to experience in my own life with NSX-T in this sense is, you definitely shouldn't overkill your architecture by starting out with bare metal edge when physical footprint or physical space is a constraint, when you don't have much idea or that enough data around your bandwidth requirements in that new environment that you are going to roll NSX out. So in that sense, there are two basic design consideration that you need to take. As Amit mentioned, bandwidth with bare metal edges, you can address more bandwidth requirement, but also convergence. But again, when it comes to SMB design, you need to take into account the physical space as well when we are talking about the bare metal edge concept. Again, on collapse cluster, obviously it has to be an edge VM. And again, as Amit mentioned, VM edge is what we are recommending in an SMB design. This category already has been mentioned by Amit, but again, With 2 PNICs, you are already limited to using a single NVDS on an ESX host by collapsing every kind of traffic on that single NVDS and leverage name teaming policies to segregate your traffic across different PNICs. With 4 PNIC design, you have more design choices. What you need to keep in mind with 4 PNIC design is if you are using vSAN, you definitely should segregate vSAN traffic and your actual north-south data plane traffic from each other. Collapse them, not collapse them, segregate them, use vSAN on VSS or VDS, use the NSX edges on top of NVDS. And also single tier or 2-tier routing. Although single tier routing may seem simple to you, believe me, been there, done that. 2-tier routing provides you extreme flexibility in the sense of tier 0 becomes a provider router, you don't touch it after day 0, and the tier 1 routers become your tenant routers or where you are instantiating your centralized services on. Really quick, last slide. I'm already running over time. On this slide, I don't want to read everything or I don't want to go through everything, but what I want to leave you out with is increased services use is a very interesting topic because based on your NSX license, you can instantiate any kind of service on top of your ESX hosts. So you still do not have to overkill the design by putting dedicated physical network appliances in your data center. You can start out small with NSX, test NSX-T's features with that specific networking function. Then if you are satisfied, if you are happy with it, you can put more intelligence onto your hypervisor layer, onto those NSX edge nodes, which means you, as soon as you scale out your compute layer by putting more ESX hosts, what's happening in the networking data plane is you are getting more data plane capacity in terms of networking functions. There are tons of resources, but we have consolidated most of them to this website, which is called NSX-T on VMware.com. And with that, please fill out a survey to get your feedback. Thank you so much.
Thank you.